Now we're getting to number 12. I'm skipping number 11 in the PDF, um, but we're getting to number 12. And I actually want to say a little bit more than number 12 says. Um, we've got this wonderful relationship, e to the it equals cosine t plus I sine t. There's a few different ways to look at it. Let me talk about what I think is the coolest way to think about it. Um, we've got a couple of definitions of e to any complex number, including I times a real number, pure imaginary. And we've been going with the perspective that we already knew and understood a fair amount about cosine and sine, and then it's a cool connection between the two concepts. And that's a great way to think about it. But in some way, it's even cooler to imagine not only have we never heard of complex numbers before, maybe we've never heard of cosine and sine before. And you don't ever have to have heard of cosine and sine. This could be the first place you ever hear about them. And you could define the cosine of a real number as the real part of e to the it, and the sine of a real number as the imaginary part of e to the it. Notice this is one of those places where it really makes sense that this m is just, it's the coefficient of I. It's not the thing with the I, because we want it to be a real number. Okay. And we already know that e to the it traces out a circle. We thought about geometry and the magnitude of this thing, and it's going around at the right speed. You can use these as the definition of cosine and sine, and you will be able to figure out everything you want to know, everything standard fact about cosine and sine. It gets even a little cooler if you then look at doing e to the minus it. Remember, this is also the same as e to the it bar. And that tells you right off the bat that this guy doesn't change because it's the real part. Okay, so cosine is an even function, so that's one thing we've determined right off the bat. And then this guy, because when you take the bar, the I does change, that turns into minus. Okay, so sine is an odd function. And here's what's super cool about that. It's that I can add and subtract these guys, and I can get the cosine t is e to the it plus e to the minus it over 2. And sine t, that's a comma in case you're wondering. Sine t, let me make sure it fits, is e to the it minus e to the minus it over 2I. And these are extremely like the definition of cosh and sinh, the hyperbolic cosine and hyperbolic sine. You just delete the i's here and delete all 3 i's here, and you get the definition of the cosh and sinh. So this is another thing that tells you, yeah, that those hyperbolic trig functions that solved, remember those solved y double prime equals lambda y for lambda positive, they are absolutely totally connected to cosine and sine. It's just the miracle of putting i's in or taking i's out. This even goes a tiny bit further, which is super cool. It allows us to define the cosine, for example, of a complex number. And then the question is sort of, why would you want to do that? And I'm not going to get into the super cool uses of that, but it really does. That's a little more advanced complex analysis. Cosine z, you just define it to be e to the iz plus e to the minus iz over 2. Now, these are no longer just e to the its anymore, so they're going to be more complicated. And sine z is e to the iz minus e to the minus iz over 2I. Just exactly the same formula, let's just put a z in. Okay, that's pretty wild. That not only is this a way to define the ordinary cosine and sine in a very cool, clever way, you can define cosine and sine of a complex number. Now, what I asked in 12 is something much more basic, which is if you just know this, how do you get, I claim you can get the sum rules for sine and cosine based on, and this is what I skipped in 11, the fact that e to the I t plus s is e to the it e to the is. And this is going to give us a beautiful derivation of the sum rules of cosine and cosine. This is something I don't talk about in like a pre-calculus class. This is something I do often, although I use the cis notation. I don't talk about the e to the I. But basically the idea, this is how I often talk about and derive the sum rules for sine and cosine. Because they're really reflections of this beautiful, super simple sum rule that's just the master property of the exponential. So this is definitely something you should do yourself. Please pause the video. But it's really just expanding out both sides, right? This is cosine t plus s plus I sine t plus s equals, and then this is cosine t plus I sine t times cosine s plus I sine s. Okay. And now I'm just going to expand that out. Okay. So we're using sort of the calculus of complex numbers that and the algebra of the exponentials, and then the basic algebra of complex numbers, and we get cosine t cosine s, and then minus sine t sine s. And if you're ever wondering, hey, is there a really beautiful, amazing, deep explanation, oops, of why that minus sign is there in the sum formula? That's a t, okay. It looked like a minus and a parenthesis put together. Let's see, this is going to be sine t cosine s plus cosine t sine s. I mean, these formulas seem a little bit weird the first time you see them, and I think especially the weirdest thing is the minus sign. The fact that the sum formula for cosine has a minus sign. Well, what is that minus sign? It's an I squared. That's a great little blow your mind thing if you're talking to somebody who's just learning this formula for the first time. Almost certainly they're not going to learn it in this way in most classes, and you can tell them secretly, deep down at the heart of things, that's an I squared. That's why this minus sign is here. So we're just identifying cosine sine t plus s is the real part, sine t plus s is the imaginary part, and we're done. It's absolutely the slickest way to derive those formulas. Okay, so I think I need more blank paper. So I think I'll skip 13 as well. Actually, no, I shouldn't skip 13. It's not that hard, and I really want to be able to talk about it. So suppose I have, oops, that's showing through. So suppose I have e to the, let's say, y of t. These are going to be the solutions to the more general problems, like the damped harmonic motion types of problems, where alpha is no longer a real number, which was what we were started out assuming we understood, and not pure imaginary either, which would give us just circular motion. Let's say alpha is a plus bi, so y of t is e to the a plus bi times t, and again I'm using the product, that fundamental property of the product of exponentials. Now I'm thinking I should insert a video to prove that in case you either don't believe it or don't want to do problem 11 yourself. It's so important. And it says eat a bit. Eat a bit. I like that. So what is this going to look like? It's not too hard to analyze. This guy, we know that just goes around a circle. E to a pure exponential or pure imaginary times t, that traces out a circle. That's the fundamental coolness of this whole thing. And then e to the at, that just grows or decays. Okay, so let's say, to be specific, let's say a and b are greater than 0 to start out. Okay, and e to the 0, of course, is 1. It's going to start at 1. And now this is going to go counterclockwise, and then this is going to make this is going to be a unit complex number, and that's going to be a magnitude. So in fact, this is already expressed in this polar form, r e to the I theta. The theta is bt, and the r is the e to the at. So it's going to be an exponential spiral. So it goes out. This is for a being fairly small, because otherwise, because notice as t goes from 0 to, well, depends on what b is. Let's say b is 1 for a second. Then in 2 pi, it'll do this. And then this factor, this ratio, is e to the at. So in fact, this would be e to the at. So that's going to be one case. And then you can think about how many other different cases there are going to be. They're going to be based on the signs of a and b. So it could be spiraling counterclockwise or clockwise, outward or inward, or a very special case could be a circle. That's going to be where a equals, what is it? Yeah, a equals 0. Okay. B equals 0 would just start out, would just, of course, be just pure purely real and would just go out radially. So this encompasses a lot of good behavior. And that's very important to think about for the analysis we're going to see for harmonic motion. And now we're finally ready to attack a totally realistic version of our core problem. And since we're at 10 minutes, we'll do that in the next video. But I'm sure you can't wait.